Right now, in two separate laboratories in Texas, devices are generating electricity with no combustion, no solar input, no radioactive decay rods, and no mechanical motion of any kind. One harvests energy from the quantum vacuum, the baseline energy state of empty space itself. The other pulls electricity directly from nuclear reactions, occurring inside a solid chip at room temperature. Both are real. Both are published. Both have working hardware. This is not a comparison of theories. This is a comparison of two competing pathways to post-chemical energy, and we are going to go deep on the physics of both. Dr. Harold White, known as Sonny, spent years at NASA's Johnson Space Center leading advanced propulsion research. He is the same physicist who proposed a refined Alcubierre warp drive metric that reduced the exotic energy requirement by 11 orders of magnitude. He now runs Y.R. Casimir Inc., a deep tech startup in Houston, Texas, focused on nanostructured devices that generate continuous electrical power by engineering the Y.R. Casimir effect, a measurable quantum vacuum phenomenon. His most recent work, published in Meson Physical Review Research, Volume 8, 2026, provides the analytical theoretical foundation for why the vacuum behaves as a dispersive acoustic medium, and why that matters for energy extraction. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged parallel conducting plates placed nanometers apart in a vacuum would experience an attractive force, with no charge, no magnet, and no external field involved. The mechanism, quantum field theory, requires that even in a perfect vacuum, electromagnetic field fluctuations exist at all frequencies between two closely spaced plates. Only wavelengths shorter than the plate separation can fit, suppressing the vacuum energy density between the plates relative to outside. That pressure differential generates a net inward force. This is not theoretical. It has been measured to within 1% of prediction using torsion pendulums and atomic force microscopy. The Casimir force scales as 1 over the fourth power of plate separation, meaning at 10 nanometers, it becomes significant. At 2 nanometers, it dominates all other surface forces. White's insight, instead of measuring this force passively, engineer the geometry to make electrons move directionally and extract a current. White's chip etches millions of customized Casimir cavities into a silicon substrate using standard semiconductor nanolithography, the same process family used to build the transistors in your phone. Each cavity consists of two parallel plates separated by gaps in the range of 2 to 10 nanometers, with central pillars designed to prevent stiction. The catastrophic collapse of surfaces at this scale due to van der Waals and Casimir forces themselves. The pillars serve a second function. They create asymmetric boundary conditions inside the cavity. The quantum vacuum field interacts differently with the pillar geometry than with the flat walls, inducing a preferential electron flow direction, net current in the surrounding conductor. Think of it as a quantum rectifier. The vacuum fluctuations are isotropic, but the cavity geometry breaks that symmetry. Broken symmetry means a preferred direction. A preferred direction means a voltage potential across the device. Current demonstrated output, 3.5 volts in capacitive discharge mode, with select chips showing quantum steady-state current and voltage. Near-term target, a Prefiv Mumatlami X 5mm chip producing 1.5 volts and 25 microamps, sufficient for RFID, IoT sensors, glucose monitors, and key fobs. White's 2026 paper does something remarkable. It shows that if you model the quantum vacuum as a dispersive acoustic medium, right, one where the speed of sound varies with frequency, and if that medium obeys a quadratic dispersion law, written as omega equals d times q squared, where d equals h bar over 2 times the effective mass, then the acoustic wave equation of that medium becomes mathematically identical to the hydrogenic Schrödinger equation. This means the energy levels of hydrogen, the Rydberg ladder, the 1 over n squared spectrum, fall out of the vacuum acoustics problem with no quantum postulates beyond symmetry and boundary conditions. Angular momentum quantization emerges from the Laplace-Beltrami spectrum on the two-sphere. Bound states emerge from the DD stop-band condition A of omega less than 0. The Rydberg constant calibrates the single free parameter. Why does this matter for the chip? Because it means the vacuum's dispersive structure is, and not arbitrary, It is constrained by the same physics that produces atomic spectra. White is engineering a medium whose properties he can now analytically describe. Fabrice David is a French physicist and inventor who has been working in the field of key, low-energy nuclear reactions. LENR, since the early 1990s. He is affiliated with Kepler Aerospace, CAR in Midland, Texas, the same city as the Midland Spaceport, where his team also operates a Texatron hot fusion device, a rifled toroidal pinch generating neutron pulses in a vacuum chamber. David has authored over 130 scientific publications, filed numerous patents, and has presented his work at every major LENR conference including ICCF, the International Conference on Condensed Matter Nuclear Science, and IWHLM, the International Workshop on Anomalies in Hydrogen-Loaded Metals. He was recently appointed Independent Director of American Fusion, traded on OTC markets as RNWF, where he provides scientific oversight of their Texatron aneutron fusion platform. And, critically, this month, Fabrice David will be presenting his latest Kepler solid-state fusion generator advances at EYLM 17, held March 24th through 26th, 2026, at Chilometro Rosso Innovation District in Bergamo, Italy. IWHLM 17, the 17th International Workshop on Anomalies in Hydrogen-Loaded Metals, is the premier scientific conference for LENR research. It is organized by the French Society for Nuclear Science in Condensed Matter, the SFSNMC, which is a member of the International Society of Condensed Matter Nuclear Science. The venue is Chilometro Rosso, a high-technology innovation district 40 kilometers northeast of Milan, a fitting location for work that sits at the frontier of materials science and nuclear physics. Notably, the conference includes a public exhibition open to press, industry VIPs, and government authorities. Running March 23rd through 25th, researchers and companies are invited to demonstrate their working energy production devices, not just show papers. Fabrice David and Kepler Aerospace will be physically demonstrating their solid-state fusion generators. At this exhibition, this is not a talk. This is a live device demonstration in front of scientists, engineers, and decision-makers from across Europe and beyond. In 1989, electrochemists Martin Fleischmann and Stanley Pons announced that electrolysis of heavy water using a palladium cathode produced more heat than could be explained by any known chemical reaction, and detected traces of helium-4 and interneutrons consistent with deuterium fusion byproducts. The announcement was controversial. Early replication attempts failed. The field was largely abandoned by mainstream physics, but a global community of researchers continued. Over the following 3 decades, excess heat has been measured by teams at the Naval Research Laboratory, ENIA in Italy, Mitsubishi Heavy Industries, and dozens of universities. The correlation between excess heat and helium-4 production has been confirmed multiple times. What is not agreed upon is the mechanism. The standard fusion reaction, deuterium plus deuterium, requires overcoming a Coulomb barrier of approximately 100 kiloelectron volts. At room temperature, thermal energy is only a fraction of an electron volt. Classical quantum tunneling probability at this energy gap is negligibly small. LENR researchers propose that the de crystal lattice of palladium, DICE, heavily loaded with deuterium, creates local conditions, enhanced screening, coherent phonon modes, or exotic intermediate particles that effectively lower or bypass the Coulomb barrier in ways not yet captured by standard nuclear theory. A fusion diode in David's construction is structurally simple. A silicon semiconductor wafer is coated on one face with a palladium layer, deposited by vacuum sputtering. the same technique used in semiconductor fabrication and optical coating. The reverse face receives a gold contact layer. The palladium is then loaded with deuterium, either electrochemically by electrolysis of heavy water or by gas phase absorption at elevated pressure. Palladium has an unusual property. It absorbs hydrogen isotopes into its face-centered cubic lattice at a palladium to deuterium ratio approaching 1:1. One of the highest hydrogen loading capacities of any metal. At the palladium-silicon junction, an electric field forms naturally, analogous to the built-in potential of a PN diode junction on the order of 1 megavolt per meter across a 1 micrometer junction width. David has noted that this intense electric field may itself contribute to compressing deuterium nuclei in the junction region, creating what researcher Edmund Storms calls a nuclear active environment, a local condition where anomalous nuclear reactions become possible. The device requires no external electrical input, K. It is self-polarizing from the moment it is assembled. Here is the key physics that makes the fusion diode concept work, and it hinges on a process proposed by MIT physicist Peter Hagelstein. In conventional deuterium-deuterium fusion, the reaction produces helium-4 and releases 23.8 million electron volts of energy, predominantly as a de-prompt gamma ray. That gamma ray is what makes hot fusion dangerous and what makes conventional fusion reactors require massive shielding. Hagelstein's theoretical work, supported by experimental evidence from Metzler, Hagelstein, and Liu, published in the Journal of Condensed Matter Nuclear Science in 2018, proposes that in a loaded metal lattice, this 23.8 MeV of nuclear energy can be transferred incrementally into the phonon modes of the lattice, rather than emitted as a single gamma photon. The lattice, in essence, downconverts one high-energy photon into millions of low-energy lattice vibrations. Each vibrational quantum, each phonon, carries only a few electron volts of energy. A few electron volts is precisely the energy scale of semiconductor band gaps. Silicon has a band gap of 112 electron volts. A phonon at a few eV can excite an electron across that band gap, creating a free electron-hole pair, exactly as a photon does in a solar cell. If this excitation happens at or near the palladium-silicon junction, the built-in electric field separates the electron and hole. The electron flows through the external circuit. Current flows. Power is generated. What has actually been measured? Professor Jean-Paul Biberian at the Faculty of Sciences in Marseille tested one of David's early silicon powder, palladium powder diodes, sealed in a pressurized hydrogen atmosphere inside a metal container. His data showed an initial voltage drop followed by asymptotic stabilization at approximately 0.5 volts. Over several days of continuous operation, David's own team has demonstrated our reproducible 0.4 volt outputs from palladium black deposited on copper sheets with a copper counter electrode separated by polyester gauze wound into sealed tubes under hydrogen atmosphere. The team at BioLife in Sarasota, Florida, led by Charles Entenmann, went further, testing over 1,500 combinations of semiconductor and metal materials. Their most striking discovery, now termed the Entenmann-Gordon effect, is that replacing the semiconductor layer with ordinary paper or asbestos fabric still produces a measurable voltage and current. The semiconductor junction is not strictly required. The energy is being generated at the palladium-hydrogen interface itself. This finding was independently replicated by Frank Gordon and Harper Whitehausen in the United Kingdom, who built a device they call the lattice energy converter, a tube coated with nanocrystalline palladium inside a concentric tube filled with hydrogen gas. Their device generates a continuous 1 microwatt net of power. David's team has since replicated the Gordon-Whitehouse LEC design in sealed glass tubes, with consistent results. A discovery is worthless if it cannot be manufactured at scale. David has addressed this directly. His team has built an electrolytic deposition apparatus that continuously coats thin metal sheets, copper or other substrates, with palladium black nanocrystals at a throughput of 4 centimeters per hour. The sheet feeds from a supply reel, passes through the deposition bath, dries over half a day, and winds onto an output reel. The coated sheets are then die-cut into discs of the desired diameter, stacked in series inside sealed tubes under hydrogen atmosphere, and the stacked voltage is summed. David's team has already stacked enough diodes in series using a Faraday voltage boosting converter circuit to illuminate LEDs. The LEDs shown at his IWH-LM16 poster in Strasbourg 2024 were powered entirely by palladium-hydrogen solid-state fusion diodes. Current power output per unit cell is in the 10 microwatt range. Modest but critically, this is not excess energy above an input. There is no input. This is energy directly generated with no external power source. David works with 2 theoretical frameworks to explain the LENR mechanism in his diodes. The first, developed by physicist John Brandenburg, is the D-Pomeroy model. In high-energy physics, the pomeron is a particle exchange that mediates the strong nuclear force at large distances, but pomerons typically appear only at high energies. Brandenburg proposes a virtual pomeron, a pomeroid, that could mediate strong force interactions at low energy inside a dense, structured lattice, effectively extending the range of the strong nuclear force and enabling fusion at sub-barrier energies. The second hypothesis is David's own concept of diffluidité, from the Greek for through and liquid, built on the physics of discrete breathers. In a crystal lattice, the Boltzmann distribution applies to gases and liquids, but inside large macromolecules and metallic lattices, thermal energy does not distribute uniformly. It can localize at specific lattice sites called discrete breathers, where vibrational amplitude is anomalously high. David proposes that adjacent to these breathers are depleted zones, sites he calls freezers, where thermal energy is locally very low and quantum effects dominate. In these freezer sites, nuclear reactions become accessible without the thermal energy required classically. Both models remain unconfirmed by mainstream nuclear theory, but both are internally consistent and generate testable predictions. Now let's step back and look at what these 2 technologies genuinely share, because the overlap is more profound than it might appear. First, both are solid state. No moving parts, no thermal cycle, no combustion chamber. Both sit closer to a semiconductor device than to any conventional power generator. Second, both perform direct energy to electricity conversion, bypassing the Carnot efficiency limit that constrains every heat engine. A heat engine converting nuclear or vacuum energy to heat, then heat to work, then work to electricity would lose 60% or more in each conversion. Both of these devices skip that chain entirely. Third, both are fabricated on silicon substrates using thin film and nanoscale deposition techniques compatible with existing semiconductor infrastructure. Fourth, both are explicitly designed for deep space applications, where solar panels fail and chemical batteries are too heavy. David's abstract explicitly references powering ion thrusters. White's chip targets the same low-power sensor market. Fifth, and most deeply, both implicitly treat the quantum vacuum as an engineerable medium. White does this explicitly. His 2026 paper models the vacuum as a dispersive acoustic continuum. David does it implicitly. The LENR mechanism in a palladium lattice may involve vacuum polarization, coherent phonon-vacuum coupling, or modified zero-point fluctuations at the metal surface. The theoretical divide between vacuum energy and lattice nuclear effects may be smaller than it looks. The differences are equally important. Energy source. White draws on the quantum vacuum, theoretically inexhaustible, present everywhere in the universe, requiring no consumable. David draws on deuterium loaded in palladium, a nuclear fuel that will, over a very long timescale, deplete. Theoretical clarity. White's mechanism has a clean published mathematical framework in a peer-reviewed journal. The Casimir effect is established physics. The disputed question is whether net energy extraction is thermodynamically permitted. David's mechanism produces repeatable results, but the nuclear physics explanation remains contested in the mainstream literature. Replication depth. David's diode results have been independently replicated by at least 4 separate teams across 3 countries over 30 years. White's chip is newer, DARPA-funded, but with fewer independent replications so far. Power output maturity. David's devices are producing our steady, usable DC voltage right now. Lighting LEDs, powering sensors, White's devices are achieving high-voltage capacitive discharges, but steady-state continuous output is still being characterized. Controversy profile. David carries the stigma of the cold fusion label, a reputational burden regardless of experimental results. White operates under the Casimir branding, backed by DARPA and physical review publication, with less institutional friction. Let's answer the scaling question with specificity. In the near term, the next 3 to 5 years, David's fusion diodes have the clearer path to practical scale-up. Here is why. The bill of materials is accessible. Silicon wafers, palladium, deuterium, or hydrogen gas, copper sheet, no exotic substrates, no atomic precision lithography, no cryogenics. The DAO manufacturing process is already being developed. David's roll-to-roll palladium deposition system, producing coated sheets at 4 centimeters per hour, is a real prototype of an industrial production line, not unlike how thin-film solar cells are manufactured. The junction physics is understood. At the semiconductor level, even if the nuclear mechanism is not fully theorized, engineers can optimize geometry, loading pressure, palladium crystal structure, and semiconductor bandgap selection. And the work of Entenmann's team across 1,500 material combinations has already generated a substantial empirical dataset for that optimization. The target application is well matched. Devices generating 1 to 10 microwatts are directly useful for deep space sensor packages, distributed IoT nodes, and medical implants, markets that exist today and that would accept an exotic power source if reliability can be demonstrated. In the long term, 10 to 25 years, White's Casimir chip has the more transformative scaling potential. Contingent on resolving the thermodynamic question, here is the decisive advantage. No fuel. A Casimir chip sitting on a table in a sealed vacuum generates voltage indefinitely, not because it has stored energy, but because it is coupled to the ground state of the quantum field, which is not depleted by extraction in any conventional sense. Whether this constitutes true energy extraction or is a one-time release of a metastable state is the open theoretical question. If the energy extraction is sustainable, the Gazam-Box manufacturing infrastructure already exists at scale. Standard CMOS semiconductor fabs can produce billions of nanoscale structures per wafer. The same lithographic process that makes a 3-nanometer transistor can define a 5-nanometer Casimir cavity. White's chip is not constrained by exotic materials. It is constrained only by design rules and vacuum packaging. The output per unit area could scale dramatically with cavity density. If millions of cavities per square centimeter each contribute a fraction of a picoamp, the aggregate current at chip scale becomes meaningful. This is exactly how modern solar cells work. Billions of electron hole pairs summing to a watt. White's chip, if it performs, scales with Moore's law logic. Smaller features, higher density, more power per area, cheaper per unit over time. There is a deeper theoretical question that connects both technologies, one that White's 2026 paper begins to address. If the quantum vacuum around a proton is a dispersive acoustic medium, as White's model shows, then the vacuum is not featureless. It has spatial structure determined by the masses and charges embedded in it. Near a proton, the vacuum density profile scales as gamma over r to the 4th power. Near the surface of a palladium lattice loaded with deuterium, the vacuum would similarly be structured by the periodic nuclear charge distribution of the lattice. This suggests that LENR in a palladium lattice is not happening despite COT. The quantum vacuum. It may be happening through the quantum vacuum. The lattice may be creating local regions where the vacuum's dispersive response shifts the effective Coulomb barrier. The same mechanism White models producing the atomic spectrum, now applied at the nuclear scale inside a crystal. In other words, David's fusion diodes and White's Casimir chip may ultimately be two engineering approaches to the same underlying physics. The structured, responsive, causal quantum vacuum first articulated in White's Madelung hydrodynamics framework. Neither team has made this connection explicitly, but it is there in the mathematics. The significance of the Bergamo conference this month cannot be overstated for the LENR field. IWHLM 17 includes a FOW public-facing exhibition, open to press, industrial VIPs, and government authorities, specifically for demonstrating working energy devices. This is not a poster session. This is a technology demonstration floor. Fabrice David and Kepler Aerospace will be presenting their Kepler solid-state fusion generators advances, including the latest results on the Entanglement-Gordon effect replications, the roll-to-roll palladium deposition system, and stacked diode assemblies. The conference is organized by the SFSNMC, a member of the International Society of Condensed Matter Nuclear Science, and draws the leading LENR researchers from France, Italy, Japan, the UK, and the United States. For anyone watching this who works in energy, aerospace, deep tech investment, or materials science, Bergamo on March 24th through 26th is where the most advanced publicly demonstrated LENR hardware in the world will be on display. The address is Via Stezzano 87, Bergamo, Lombardy, Italy, Chilometro Rosso. We are standing at a genuinely unusual moment in the history of energy science. Two independent research programs, one grounded in quantum vacuum engineering, one in condensed matter nuclear physics, are converging on the same destination: solid-state, solid fuel-free, or low-fuel electrical generation at the chip scale. Harold White's Casimir chip offers the theoretically limitless ceiling, a device coupled to the ground state of spacetime itself, manufacturable on existing silicon fabs, with a rigorous mathematical foundation now published in Physical Review. Fabrice David's fusion diodes offer that near-term demonstrated path than 30 years of iterative refinement, multiple independent replications, a scalable deposition process, and live hardware demonstrations happening this month in Bergamo, Italy. The question is not which one is real. Both are producing measurable outputs from non-chemical, non-thermal sources. The question is which one reaches the engineering threshold of 1 milliwatt per square centimeter. First, the point at which practical applications become commercially viable. Whoever gets there first will not just change how we power satellites, they will change how we power everything. The source papers are in the description. The Bergamo exhibition is in 2 weeks, and the frontier is open. But let's take a moment to say something that gets lost in the technical details. We live on a planet of 8 billion people. Nearly 700 million of them have no reliable access to electricity. Hundreds of millions more live with intermittent power, expensive fuel, and energy systems that are poisoning the atmosphere that all of us share. Every war fought over oil, every child doing homework by candlelight, every satellite that goes dark because its solar panels failed, every deep space mission we could not afford to fly because we could not solve the power problem. Both of these technologies, if they scale, erase those constraints. A Casimir chip embedded in a medical implant that never needs a battery change. A fusion diode powering a village water pump in a place the grid will never reach. A Kepler solid-state generator keeping a deep space probe alive past the orbit of Neptune, decades into its mission, still transmitting. We are not talking about a better battery. We are talking about energy that is everywhere, because the quantum vacuum is everywhere. We are talking about energy from the structure of matter itself, available to anyone who can build a palladium-coated chip. Humanity has been extraordinarily lucky in its history with energy. Coal powered the Industrial Revolution, oil powered the 20th century, and the atom gave us a glimpse of something deeper. But every one of those sources came with costs we are still paying. These technologies, White's Casimir chip and David's fusion diodes, ask for almost nothing in return. No mining, no combustion, no waste, no geopolitics of fuel. We should be rooting for both of them, EZU, with everything we have, not one over the other. Both, to the nth degree, to full commercial scale, to gigawatts, to the stars. Because if even one of these succeeds, truly scales, it is not just a new energy source. It is the foundation of a civilization that no longer has to choose between powering itself and preserving itself. That is worth every experiment, every conference in Bergamo, every sealed glass tube with a palladium electrode sitting in a lab at midnight generating a fraction of a microwatt. Every fraction of a microwatt is a step toward everything. The frontier is open, and humanity deserves to cross it.